A human body drifting beyond Earth would not explode, freeze solid in a moment, or vanish into darkness. The first changes would be quieter and stranger. With no pressure outside, gases would expand, exposed moisture would begin to boil away, and the brain would lose its oxygen within seconds. Yet, death would only begin the story. Without insects, weather, or air, decay would follow unfamiliar rules, as radiation and microscopic impacts altered what remained. The outcome would depend on whether the body faced a star, stayed sealed inside a suit, or continued unprotected through interstellar darkness. So tonight, the question is simple. What really happens to a human body left in deep space? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If a human body were sent into deep space as a final memorial, what one object would you place beside it to represent life on Earth? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about what really happens to a human body left in deep space. The moment begins with something almost too simple to notice. A boundary disappears. 1 second, the body is surrounded by a controlled atmosphere, held at a pressure that human organs have depended on since birth. The next, a damaged suit, an open hatch, or a broken wall connects that small protected space directly to the vacuum outside. Air does not remain calmly in place. It rushes toward the opening, carrying heat, loose objects, and a brief storm of sound with it. Then, once the remaining gas has escaped, the sound ends. Beyond the failing spacecraft, there is no air to carry it, and the emergency continues in silence. Films often turn this moment into an explosion. The body bursts, freezes, or is torn apart before there is time to understand what happened. The reality is less theatrical, but in some ways more unsettling, because the body remains recognizably human. Skin is stronger than it appears. Blood vessels, muscles, connective tissue, and the walls of the organs all provide structure, so the pressure inside does not simply blow a person apart. There would be swelling, discomfort, and serious injury, but not the violent destruction that fiction usually shows. Vacuum does not pull with some mysterious force. It is simply the absence of outside pressure, allowing gases and liquids within the body to behave in ways that ordinary air normally prevents. That difference matters because pressure is not something we usually feel. At sea level, the atmosphere presses on every part of us, yet the pressure inside the body pushes back, leaving us unaware of the balance. Our lungs, ears, sinuses, and digestive system all contain gas at roughly the pressure of the environment around them. If the outside pressure falls slowly, some of that gas can escape and the body can adjust. If it disappears almost at once, the gases already trapped in suddenly have room to expand. The emergency is therefore not created by space entering the body. It begins with the body's own air trying to get out. The lungs are the most urgent example. A natural instinct might be to take a deep breath and hold it, as though preparing to dive beneath water. In a vacuum, that reaction would make the danger worse. Water pushes inward more strongly as a diver descends, compressing the gas in the lungs. Sudden decompression does the opposite. The gas expands outward, and if the airway is closed, delicate lung tissue can tear. Air may be forced into places where it does not belong, entering the chest or even the circulation. The safest response in the impossible few seconds available would be to let the air escape, rather than trap it. But an accident violent enough to expose someone to space may offer no warning and no time for a careful response. Even with an open airway, exhalation would not feel like an ordinary breath. There is no surrounding atmosphere waiting to receive a gentle stream of air. The pressure difference drives gas outward rapidly, emptying the lungs while the chest and diaphragm can do little to stop it. Any air in the mouth and nose follows. pressure in the middle ears and sinuses also seeks a route outward, creating pain and possible damage if narrow passages cannot equalize quickly enough. A dental cavity or a small pocket of trapped gas might hurt, but the larger threat remains the same throughout the body. A human being has been taken from an environment built around pressure and placed into one where that support has vanished. As the pressure falls lower, another unfamiliar process begins. A liquid does not boil only because it is hot. It boils when its vapor can form bubbles faster than the surrounding pressure can suppress them. On Earth, water must usually be heated to a familiar high temperature before that happens. In a mere vacuum, the boiling point falls dramatically. Moisture on the tongue, across the eyes, and along the lining of the airways can begin to boil at body temperature. Not because the person has become hot, but because there is no longer enough pressure to keep that water fully liquid. This would not resemble a pot of water on a stove. There is too little exposed moisture, and the process itself removes energy, cooling what remains. The sensation reported in accidental low-pressure exposure has been described as moisture beginning to boil on the tongue, a strange detail that captures how quietly the rules change. Tears would not shoot away as clouds of steam, and the body would not instantly lose all its water. Most of that water is held within cells, tissues, and vessels, where surrounding structures continue to exert some pressure. The exposed surfaces respond first, while deeper fluids remain contained for longer. The blood, in particular, would not begin boiling through every artery and vein. The circulatory system is closed, and the pressure created by the heart, vessel walls, and surrounding tissues helps keep blood liquid. If circulation continues briefly, it still operates inside a physical container. That does not make the situation safe. At very low external pressure, water vapor and gas bubbles can form in some tissues and fluids, contributing to swelling in a process known as ebullition. But this is not the same as the entire bloodstream turning to vapor. The distinction removes one dramatic image and replaces it with a slower one, the body enlarging as vapor forms within soft tissues while its outer structure continues to hold. The swelling could be significant, changing the shape of the face and limbs, but human tissue is elastic enough to resist complete rupture. Clothing or a partially intact suit might restrict some areas while allowing others to expand. The result would depend on how quickly the pressure was lost, how much protection remained, and whether recompression followed. Even here, there is no single perfect image of what a person would look like. A small puncture in a suit, a catastrophic tear, and an open spacecraft hatch all lead toward vacuum, but they do not bring the body there at exactly the same speed. For someone directly exposed, however, the final pressure drop is enough. The body's surface is no longer warmed or cooled by moving air. This is why freezing is not immediate. On a winter night, cold air carries heat away from skin. In water, heat can be removed even faster. Vacuum has almost no matter to perform that exchange, so the body can lose heat mainly by emitting radiation and by the evaporation of moisture. Both processes take time. The skin may cool where water is boiling away, but the person does not become a block of ice in seconds. Their core still contains the heat it carried from the spacecraft, even as the environment has become fatal for an entirely different reason. Nor would the eyes explode. They are fluid-filled structures protected by strong outer layers, and although low pressure could cause swelling and damage, they would remain in place. Keeping them open might expose their moist surfaces to evaporation and boiling, adding pain and blurring. But closing the eyelids would not solve the deeper problem. The same is true of the rest of the body. Many individual tissues are surprisingly capable of surviving a brief disturbance. The danger comes from the entire system losing the conditions that allow those tissues to work together. The difference between exposure and instant destruction is more than a technical detail. It means that a very brief vacuum accident can, under controlled circumstances, be survivable if pressure is restored quickly enough. Knowledge comes partly from laboratory research, animal studies performed during the early space age, and rare accidents in pressure chambers. Those records cannot reproduce every possible event in space, and no responsible experiment would deliberately take a person to the point of death. Still, they reveal a narrow interval in which the body is badly stressed, but not yet beyond rescue. One well-known chamber accident occurred while a technician was testing a spacesuit in a near-vacuum environment. A pressure failure exposed him suddenly. He remained aware only briefly, and his last clear memory was the moisture on his tongue beginning to boil before he lost consciousness. The chamber was repressurized, and he survived without the cinematic injuries people might expect. The incident is often retold because it provides a rare human glimpse into vacuum exposure, but it should not be mistaken for proof that the experience is harmless. His survival depended on rapid intervention in a facility designed to restore pressure. A person drifting outside a spacecraft would not have a chamber crew ready to reverse the event. What remains consistent is the order of the central threats. Pressure disappears. Gas expands. Exposed water begins to change state. The lungs empty, and no new oxygen enters. For a short interval, the circulation continues using what is already present in the blood. The heart does not need outside air pressing on the skin in order to beat, and the brain does not shut down merely because it sees a vacuum. Both continue until the chemistry that supports them begins to fail. That interval is brief enough to make the event terrifying, but long enough to make it human. The exposed person would not become an object the instant the hatch opened. There may still be awareness, vision, sensation, and perhaps a moment of deliberate action. A hand might reach for a tether or a closing control. Training might overcome panic long enough to exhale. If another astronaut were close, a rescue attempt could begin. Yet every movement would consume oxygen, and the body would be unable to replace any of it. If the person wore a suit, the event might unfold through layers rather than all at once. Modern pressure suits are not simple balloons. They use strong restraint materials to keep their shape, joints that permit movement, seals around connections, and systems that provide oxygen while removing carbon dioxide and heat. A puncture may cause a leak rather than immediate total collapse, and emergency equipment may offer a limited chance to respond. A major tear, failed visor, or disconnected life support line would overwhelm that protection far more quickly. In each case, the suit's remaining pressure determines when the body truly meets the vacuum. Once it does, the suit cannot change the fundamental rules. It may slow the loss, constrain swelling, preserve warmth, or retain a small amount of oxygen for a few more moments, but it cannot make exposed human tissue independent of pressure. A glove, boot, or sealed section might remain pressurized even while another area is compromised, creating uneven forces and injuries. The transition could be partial before it became complete. This makes the real event less visually simple than fiction, though the destination is the same if the leak cannot be stopped. The body's response also reveals why an atmosphere is more than something to breathe. It holds liquid water in a stable state, permits the lungs to exchange gases, and provides an external pressure against which countless biological structures have developed. Gravity may be absent inside an orbiting spacecraft, but pressure remains. Astronauts can live in weightlessness because their cabin preserves the chemical and physical environment their organs require. Remove gravity, and the body adapts. Remove usable pressure and oxygen, and the margin becomes measured in moments. For all the strange effects of vacuum, the most decisive change is therefore almost invisible. It is not the swelling or the boiling moisture, not the silence outside, and not the distant cold. It is the end of gas exchange in the lungs. Blood arriving there can no longer collect a fresh supply of oxygen. Instead, Oxygen already in the body continues moving into tissues that are consuming it. The brain, with its constant demand for energy and almost no ability to store oxygen, is especially vulnerable. At the instant of decompression, however, that supply has not yet reached zero. Oxygen remains bound to hemoglobin in the blood and dissolved in small amounts throughout the body. The heart may continue circulating it, even as the lungs stand empty. This residual reserve creates the narrow separation between exposure and unconsciousness, between a person who might still be rescued and a body that has begun an irreversible journey. The pressure may vanish in an instant, but consciousness does not. And those remaining seconds are where the story becomes far more human. For a brief interval, the person is still present inside the emergency. The lungs can no longer provide useful oxygen, yet the blood leaving the heart still carries part of the supply gathered before the pressure disappeared. That blood continues through the arteries and reaches the brain, allowing thought and movement to persist for a little longer. The body has not found a way to live in vacuum. It is simply spending the last oxygen it already owns, and it is doing so far faster than most people would expect. The brain is especially demanding. Although it makes up only a small part of the body's mass, it requires a constant flow of oxygen and fuel to maintain electrical activity, awareness, memory, balance, and control of the muscles. It keeps almost no meaningful oxygen reserve of its own. Under ordinary conditions, this weakness is hidden because every heartbeat brings another supply. Once the lungs stop renewing the blood, circulation becomes a delivery system that is steadily emptying itself. Each pass through the brain leaves less available for the pass that follows. This creates what aerospace medicine calls the time of useful consciousness. The phrase does not describe how long the eyes remain open or how long scattered brain activity continues. It means the period during which a person can still recognize the danger, make a decision, and perform an action that might save them. At very low pressure, that period may be only around 10 seconds, sometimes a little more and sometimes less. It is not a generous rescue window. It is the fading edge of one. Even those seconds would not all be equally clear. At the beginning, an astronaut might understand that a seal has failed, see a warning light, or feel the air leaving the suit. A trained response could begin almost automatically. Exhale, locate the leak, reach for an emergency control, pull toward an airlock, or signal a nearby crewmate. But as oxygen levels fall, judgment and coordination begin to fail before the person necessarily realizes that anything has changed. A simple task can become difficult at precisely the moment when it matters most. Hypoxia, the condition created when tissues receive too little oxygen, can be deceptive. People exposed to low oxygen conditions do not always feel a clean, obvious descent toward unconsciousness. Some notice narrowing vision, tingling, warmth, dizziness, or a sense that their thoughts are slowing. Others may become unusually calm, confused, or even briefly euphoric. Fine movements lose accuracy. Numbers and procedures that were familiar moments earlier stop making sense. The mind required to diagnose the problem is itself one of the first systems being impaired by it. Activity shortens that reserve. A person pulling hard against a tether or trying to force a hatch closed asks the muscles to use more oxygen, while fear raises the heart rate and increases demand throughout the body. Remaining perfectly still would not make vacuum survivable, but intense movement can spend the final supply more quickly. This creates a cruel balance. Rescue may require immediate physical action, yet the effort needed to perform it helps narrow the time in which the action remains possible. Loss of consciousness is therefore more like a system falling below the level required to coordinate itself than a decision to sleep. Muscle control disappears. A hand that had almost reached a valve may drift away. The body may become limp inside a suit or remain held by straps in a seat. If it was moving outside a spacecraft, that motion continues, because unconsciousness changes biology, but not momentum. From a distance, almost nothing about the figure may reveal the exact second at which the person ceased to be aware. Inside, the heart can continue beating after consciousness is gone. It has its own electrical rhythm and does not require a conscious command for every contraction. For a time, it circulates blood that is becoming increasingly poor in oxygen. The brain is still biologically active at some levels, but organized awareness has disappeared. This distinction matters because unconsciousness is not necessarily death. If pressure and breathable oxygen return quickly enough, circulation may once again carry oxygen to the brain, and a person may recover. The possibility of recovery is supported by rare pressure chamber accidents and by older research conducted to understand emergency decompression. Those records suggest that extremely brief exposure can be survived when repressurization begins quickly. They also show why a single dramatic countdown is misleading. Starting oxygen levels, the speed of pressure loss, lung injury, physical activity, body size, health, and the exact moment of rescue all affect the outcome. Around 10 seconds of useful consciousness is a practical guide, not a law written into every human body. Repressurization would need to restore more than air around the skin. The lungs must again receive gas at a pressure from which oxygen can enter the blood. The airway must remain open. The heart must still move blood effectively, and any damage caused during decompression must be treated. If the person held their breath and the expanding gas tore lung tissue, oxygen may not travel normally even after the cabin is safe. Air bubbles entering the circulation can create another emergency. A rescue completed in seconds may therefore be only the beginning of medical care. On Earth, emergency medicine often speaks of minutes without normal oxygen delivery, because cardiac arrest usually occurs in an atmosphere where rescue breathing, chest compressions, and defibrillation can be attempted. Vacuum adds another requirement before any of those measures can work. The environment itself must be made survivable. A rescuer cannot simply remove a helmet or begin treatment in open space. The exposed person must be sealed into a pressurized volume, connected to a working suit system, or brought through an airlock whose cycle may take precious time. That delay makes distance inside space surprisingly important. A crewmate may be only a few meters away, yet unable to reach the person. Secure them and restore pressure before useful consciousness is gone. An airlock door may be visible but require deliberate movements and a pressure cycle. A spacecraft can appear close enough to touch while moving on a slightly different path that carries it farther away each second. The medical window and the physical rescue window are not the same, and both must remain open for survival. History offers one of the clearest and saddest examples from inside a spacecraft. In 1971, the 3 cosmonauts of Soyuz 11 were returning to Earth after living aboard the first space station. During the separation of their spacecraft modules, a pressure equalization valve opened far above the atmosphere. Cabin air escaped through an opening that should not have been exposed until much later in the descent. The capsule continued flying automatically, but the people inside suddenly faced a failure no automatic landing system could repair. Evidence indicates that the crew tried to respond. They had procedures, controls, and a spacecraft still capable of reaching the ground. But the valve was difficult to close and pressure fell too quickly. They were not wearing pressure suits. As the cabin lost air, they rapidly lost consciousness and died before the capsule returned to an atmosphere that could support them. Recovery teams reached a spacecraft that had landed normally and found its crew still strapped into their seats. The vehicle had survived the journey. The narrow biological window inside it had not. Soyuz 11 does not provide a perfect second-by-second model for every vacuum accident. The cabin depressurized over time rather than exposing the crew through a fully open hatch. and later accounts have differed over some details of the final sequence. What it demonstrates with painful clarity is the mismatch between human survival and spacecraft time. A capsule can continue functioning for minutes, orient itself, descend, deploy parachutes, and touch the ground safely. The brain cannot wait for the machine to finish that process once oxygen pressure has collapsed. After consciousness fades, oxygen stored in the blood continues to fall. Brain cells can maintain their normal electrical balance only by spending energy. Without enough oxygen, their ability to produce that energy declines. The controlled movement of charged particles across cell membranes begins to fail. Communication between neurons becomes disordered, and swelling can develop. These changes are microscopic, but together they mark the transition from a temporarily silent brain to an injured one. There is no universal second at which that injury becomes irreversible. Temperature, circulation, prior oxygen levels, and individual biology all matter. Cooler tissue may use energy more slowly, while exertion and heat can increase demand. A heart that continues pumping provides a different situation from one that has already developed a fatal rhythm. For this reason, medical language is more cautious than the clean timelines often given in popular stories. Risk rises rapidly, but nature does not place a visible line across the clock. As oxygen deprivation continues, the heart itself begins to suffer. Its muscle needs energy to maintain regular contractions, and its rhythm can become unstable. Blood pressure falls, reducing the flow that still reaches the brain and other organs. This creates a worsening loop. Low oxygen weakens circulation. Weaker circulation delivers even less oxygen, and the remaining systems lose the ability to recover on their own. Eventually, the heart stops producing an effective flow of blood. At that point, restoring cabin pressure alone would no longer be enough. Resuscitation would be required, performed in an environment where the patient and rescuer may be floating, and ordinary equipment behaves differently. Even if circulation returns, the brain may have been without adequate oxygen long enough to leave permanent injury. Survival is not merely a heartbeat restarting. It also means preserving the network that held memory, personality, awareness, and the ability to wake again. This makes the phrase "death in space" less simple than it sounds. Death is not one event experienced simultaneously by every cell. Consciousness disappears early. Because the brain is highly sensitive, circulation may continue briefly, then fail. Some tissues remain alive for longer than the person as an integrated whole. Skin cells, connective tissue, and microorganisms within the body do not all stop at the same instant. The human being is lost before every living process inside the body has ended. If no rescue is possible, the emergency gradually ceases to be an emergency. There is no longer a decision to make, a procedure to follow, or a sensation to endure. The body remains warm for a time, still carrying chemical gradients and cellular activity inherited from life, but those processes are no longer coordinated by a conscious organism. The silence outside has not changed. What has changed is the meaning of the figure drifting within it. This is where the story begins to move beyond the final seconds of oxygen. On Earth, death immediately places a body inside a busy world of air, moisture, microbes, insects, gravity, weather, and changing temperature. Those forces begin shaping what happens afterward, often before anyone can see their work. Deep space offers almost none of the same surroundings. It does not provide soil, rain, scavengers, or a breathable atmosphere. Yet the body is not chemically empty, and it does not become permanent merely because life has ended. Enzymes remain inside cells. Bacteria remain in the digestive system and across the skin. Water is still held through organs that have lost circulation, and gases are still present in spaces that no longer regulate themselves. Some processes that began during life stop quickly, while others continue without control. The familiar boundary between a living person and inert matter has been crossed, but the material left behind is still capable of changing. The final heartbeat, therefore, does not end the physical journey. It only removes the system that once repaired, damaged, moved fluids, controlled temperature, and kept countless microorganisms in balance. From that moment, the body must respond passively to whatever environment surrounds it. And in deep space, that environment follows rules unlike any grave on Earth. Once the last organized activity fades, the question is no longer how the body tries to survive the vacuum, but what can happen to it when life has stopped, and the natural world of Earth is no longer there to receive it. On Earth, a dead body never truly lies alone. Even in a sealed room, it remains surrounded by air, moisture, warmth, microbes, and materials that exchange heat with it. Outdoors, the surrounding world becomes still more involved. Insects arrive, animals may disturb the remains, rain adds water, sunlight warms the surface, and soil receives the fluids and nutrients released from the tissues. What we call decomposition is not one process working by itself. It is the result of the body and its environment changing one another. Deep space removes most of those partners. There is no soil beneath the body, no weather passing over it, and no insects able to find it. Beyond a spacecraft or suit, there is almost no pressure and almost no surrounding matter. Yet decomposition does not wait for an outside creature to begin. The body brings its earliest agents of change with it, hidden inside the same cells and organs that kept it alive. During life, each cell maintains a carefully controlled interior. Membranes separate one chemical region from another. Proteins are repaired or replaced, and enzymes that can break down biological material are kept in the places where they are useful. All of this requires energy. When oxygen delivery and circulation end, energy production falls. The membranes begin to lose their integrity, and the control that kept destructive reactions contained slowly disappears. Enzymes then begin acting on the tissues around them. This self-digestion is called autolysis, although the name makes the process sound more deliberate than it is. Nothing has started eating the body in the ordinary sense. Cellular structures are simply no longer maintained, and chemicals once used for normal tasks begin breaking apart membranes, proteins, and other components. The body has stopped repairing the tiny damage that life was constantly creating. Autolysis does not advance at the same speed everywhere. Organs rich in enzymes and water tend to change earlier, while tougher connective tissues resist longer. The lining of the digestive system, the pancreas, and other soft organs are particularly vulnerable. Skin, tendons, and bone follow different timelines because their structures and chemistry are different. Even before the environment takes a major role, the body is already becoming uneven. Some regions change quickly, while others remain close to their previous form. The loss of circulation also removes the internal transport system that once balanced temperature, chemistry, and immune protection. Blood no longer carries heat from one area to another in the same way. Waste products are no longer cleared. The immune cells that helped keep microorganisms confined can no longer coordinate a defense. Boundaries that seemed permanent during life begin to weaken, and this opens the way for another community already present inside the body. Trillions of microorganisms live on human skin and through the digestive tract. While a person is alive, many of them are harmless or helpful, and the body regulates where they can grow. Death changes that relationship. The intestine no longer moves normally, immune barriers fail, and microbes can spread into tissues that were previously protected. On Earth, their activity contributes to putrefaction, producing gases and breaking large biological molecules into smaller ones. The absence of outside air does not immediately stop all of them. Many microbes in the gut are adapted to environments with little or no oxygen. They do not need a breathable atmosphere around the body in order to remain active for a time. As long as liquid water, usable nutrients, and a suitable temperature remain available. Some internal communities can continue their chemistry. Vacuum may surround the skin, but the center of the body does not become a perfect vacuum at the same instant. This is an important difference between the environment outside the remains and the small environments still trapped within them. Organs, folds of tissue, the digestive tract, clothing, and any surviving layer of a suit can retain moisture and gases. The body begins as a collection of protected pockets rather than one uniformly exposed object. Each pocket changes as seals fail, water escapes, and temperature shifts, so the early post-mortem process may continue in one area while slowing dramatically in another. On Earth, microbial activity often causes gases to collect, producing the familiar bloating associated with decay. An unprotected body in vacuum would not necessarily follow that appearance. Gas that reaches an opening can escape into space, and the external pressure is too low to hold it in. Some gas may still form within enclosed tissues and cavities, at least temporarily, but cracks, injuries, and natural passages provide routes outward. The result would depend on how rapidly the body had been decompressed and how much of its outer covering remained intact. The earliest changes, therefore, do not create a normal Earth-like sequence transplanted into the sky. Autolysis may begin, microbes may spread, and gases may form. Yet the surroundings are steadily taking away the conditions that allow those reactions to continue. Moisture at exposed surfaces is lost. The body cools or heats according to radiation rather than contact with air. As internal compartments open to the vacuum, liquid water becomes harder to retain. The missing insects make an enormous difference. On Earth, flies can locate remains quickly, and their larvae consume soft tissue while creating heat and opening new pathways for microbes. Beetles and other insects may arrive later, each contributing to a recognizable ecological succession. None of that can occur in deep space, unless such organisms were somehow carried inside a sealed habitat with the body. A person exposed beyond the spacecraft is removed from the entire web of scavenging life that normally accelerates physical breakdown. Larger scavengers are absent as well. Nothing pulls apart clothing, breaks bones, exposes deeper tissue, or carries pieces away. There are no roots growing through the remains, and no rainfall moving dissolved material into the ground. Gravity may still guide the body along an orbit, but there is no surface beneath it on which fluids can pool in the ordinary way. Many visual signs used to estimate time since death on Earth would be altered, weakened, or missing entirely. Temperature adds another layer of uncertainty. The body begins close to its living temperature, and for a short period this supports enzyme activity and microbial metabolism. With no circulation, internal heat becomes uneven. In vacuum, heat cannot be carried away by surrounding air, so cooling is not instant, but radiation and evaporation gradually alter the balance. A body in sunlight, one turning between light and shadow, and one drifting through interstellar darkness, would not share the same thermal history. Cold slows many chemical and biological reactions, but cold alone does not erase them. If tissues freeze, the movement of liquid water is restricted, and microbial growth can nearly stop. Ice can also damage cells as crystals form, adding new structural injuries that become important if the tissue later warms. Repeated heating and cooling could create a cycle of partial thawing, evaporation, and freezing, although the exact result would depend on orbit, rotation, shielding, and distance from a star. Vacuum adds drying to this process. As moisture leaves the exposed tissues, enzymes lose the liquid environment in which they normally work, and microbes lose access to water required for growth. Activity slows, then may stop in large regions of the body. This does not mean every microorganism is destroyed. Some cells can survive drying in a dormant or severely reduced state, especially if protected from direct light within tissue. Experiments in space have shown that certain microbes can survive vacuum when shielded. But survival is not the same as active decomposition. The distinction matters because a body can contain living microorganisms without continuing to decay rapidly. A dry seed may remain biologically viable while showing almost no growth, and some microbes can enter similarly inactive states. Deep within dried material, a small surviving population might persist long after the soft tissue around it has stopped changing in familiar ways. If water and warmth somehow returned, some activity might resume, though a body drifting in deep space may never encounter those conditions again. What develops is not perfect preservation, but an interruption of the ordinary route towards skeletonization. On Earth, soft tissues are consumed, liquefied, dispersed, or recycled until bone becomes exposed. In space, rapid loss of water could leave dried tissue attached to the skeleton for a very long time. The body might remain recognizably human on the outside while its cells, proteins, and DNA had already suffered extensive microscopic damage. The word preserved can therefore be misleading. It suggests that the body has been held exactly as it was at death, like an untouched object placed behind glass. In reality, autolysis may already have altered organs before drying slowed it. Microbes may have moved beyond their living boundaries. Vacuum may have collapsed some tissues and expanded others, while temperature changes create fractures and distortions. The later appearance could hide a great deal of early change. There is also no direct human experiment that can provide a simple timetable. No unprotected body has been deliberately released into deep space and recovered years later for study. Scientists must combine what is known from vacuum physiology, forensic decomposition, microbial survival experiments, thermal physics, and the behavior of biological materials. Each field describes part of the outcome, but none reproduces the full journey. Any precise claim that a body would remain unchanged for a specific number of years would go beyond the evidence. Even the phrase deep space covers environments that differ sharply. A body drifting near Earth still encounters strong sunlight, passages through shadow, atomic particles in the thin upper atmosphere if the orbit is low enough, and a measurable chance of eventually re-entering. Near another planet, radiation belts, reflected light, or a thin atmosphere may matter. Far between stars, the body receives far less energy and may cool for an immense length of time. The absence of Earth does not create one universal set of conditions. The earliest post-mortem hours would depend less on that distant cosmic setting than on what immediately surrounds the remains. An uncovered body loses moisture and gas directly to the vacuum. Clothing can slow the escape from some surfaces. A container can preserve pressure, and even a damaged enclosure may hold a thin atmosphere for a while. The materials closest to the skin determine whether internal chemistry is interrupted quickly or allowed to continue. This returns the story to the equipment that had once kept the astronaut alive. A pressure suit is designed to maintain oxygen, remove carbon dioxide, control heat, and separate a person from vacuum. After death, those systems may stop, but the physical layers do not instantly vanish. The suit can still trap gases, water, heat, and microorganisms around the body, creating a small environment with no one left to regulate it. If the suit remains sealed, decomposition may continue more like it would inside a closed container than on an exposed surface, at least until temperature, pressure, and limited resources change. If it has torn open, different parts of the body may face different conditions. A visor, glove, or boot could remain intact while another section vents to space. What happens afterward depends not only on the body, but on how long this last artificial boundary continues to behave like a world of its own. The vacuum outside may be almost empty, yet a sealed suit can preserve a final pocket of Earth around the person who wore it. Inside that pocket, water can remain liquid for longer, gases can accumulate, and microbes can continue working, until their environment collapses. The suit has ceased to be a life support system, but it has not ceased to shape the fate of what it contains, and its slow transformation from shelter into enclosure is where the journey now continues. A spacesuit is often described as a small spacecraft, and the comparison is more than a convenient image. Around the astronaut is a pressure vessel shaped like clothing, supported by a portable system that supplies oxygen, moves gas through the suit, removes carbon dioxide and humidity, and carries excess heat away from the body. Its layers protect against temperature extremes and small impacts, while a strong restraint structure prevents the pressurized garment from expanding like a balloon. As long as these systems work, the person inside carries a private atmosphere through an environment that has none. Death would not make that atmosphere disappear immediately. If the suit remained intact and its valves stayed closed, gas would still press against the body, and water would remain far more stable than it would on an exposed surface. The helmet, torso, gloves, and boots would form connected pockets of air, with fabric and seals slowing their exchange with the vacuum. The boundary that had preserved life would begin preserving the conditions for change, afterlife. For a short time, the backpack might even continue operating. Pumps and fans do not know that the person has died. If power remained and the equipment had not been damaged, ventilation could keep gas moving through the helmet and around the limbs. A cooling loop might continue drawing heat from the body, while filters remove traces of carbon dioxide and water vapor from the suit atmosphere. The result would depend on how the death occurred and which parts of the system survived it. This mechanical afterlife would be limited. Batteries discharge, oxygen supplies empty, cooling water is exhausted, and filters eventually stop performing their intended work. A system designed for a spacewalk lasting hours was never meant to manage a sealed body for days or years. One function may fail before another. The fan may stop while pressure remains, or cooling may end while the garment is still sealed. The suit gradually changes from an active environment into a passive container. Inside that container, the body still begins with warmth and moisture. Autolysis continues within vulnerable organs, and microbes remain active wherever water and suitable temperatures persist. Without circulation, heat becomes uneven, but the atmosphere inside the suit allows some energy to move by contact and by flowing gas. The insulated outer layers also slow the body's exchange of heat with space. For a while, the interior can remain much closer to a closed room than to the vacuum only a few centimeters away. That closeness would be deceptive. A room has a large volume of air, surfaces that absorb heat, and often some route for gases and moisture to escape. A suit has very little free space. Everything released from the body enters a confined environment. Water vapor can collect on cooler materials. Volatile chemicals produced by tissue breakdown remain near the skin. If microbial activity produces gases faster than they are removed or leaked away, internal pressure can shift even after the life support system has stopped maintaining it. The helmet may become one of the clearest places where this enclosed chemistry appears. Warm, moist gas rising from the body can meet a visor cooled by the environment outside. Condensation may form across its inner surface, first as a film and later, under colder conditions, as frost. The same transparent shell that once gave the astronaut a view of space could become clouded from within. This would not happen in one predictable pattern, because sunlight, shade, rotation, and the remaining thermal controls all alter the visor's temperature. Moisture would also settle within fabric, joints, and the layers closest to the skin. A spacesuit includes a cooling and ventilation garment worn against the body, along with tubes, padding, communications equipment, and other materials that create narrow spaces. These surfaces can absorb or trap fluids released after death. Instead of leaving directly for the vacuum, some of the body's water moves into the suit itself, turning the clothing and equipment into part of the post-mortem environment. Microbes do not require the suit to contain breathable air in the ordinary sense. Many organisms involved in internal decomposition can work without oxygen, provided that water, nutrients, and a tolerable temperature remain. A sealed garment may therefore allow putrefaction to continue longer than it would in direct vacuum. The process would still be limited by cooling, drying, changing acidity, and the buildup of waste products. But it would not stop merely because the person outside the suit is surrounded by space. Gas produced inside the body may enlarge the abdomen and soft tissues, as it can on Earth, while additional gas enters the small volume around them. The restraint layers of the suit resist outward expansion, so pressure changes are contained by strong fabric, rings, bearings, and seals. This does not mean the suit would inevitably burst. It was built to hold pressure from within. The more likely outcome is a complicated balance between gas production, material flexibility, valve behavior, and slow leakage. Valves make that balance difficult to predict. Spacesuits contain routes for ventilation, pressure regulation, emergency purging, and connection to life support equipment. Their exact behavior depends on design and condition. A relief system may allow gas to leave if internal pressure becomes too high. A failed seal may leak continuously. A damaged hose may expose the suit atmosphere directly to vacuum. What appears from the outside to be a closed white shell may actually be losing molecules through several small paths. No pressure suit is perfectly impermeable forever. Flexible materials allow extremely small amounts of gas to pass. Seals, age, and repeated temperature changes place stress on joints and connections. During an ordinary mission, these losses are measured and managed over a limited period. During an uncontrolled drift, there is no maintenance, no replacement of a damaged glove, and no new oxygen added to compensate. Even a suit that survives the original accident begins a slow movement toward the pressure outside it. The rate of that movement matters more than the simple labels sealed or open. A catastrophic tear equalizes pressure quickly and exposes the body almost at once. A small leak can take far longer, allowing internal decomposition and moisture redistribution before the vacuum becomes dominant. A nearly intact suit might hold a thin atmosphere after much of its original gas has escaped. Different regions can also become isolated, leaving a glove, boot, or fold of fabric with conditions unlike those around the torso. As pressure falls, the boiling point of water falls with it. Fluids that remained stable inside the pressurized garment begin responding to the weakening atmosphere. Moisture on exposed surfaces evaporates more rapidly, and water vapor moves toward leaks. Evaporation removes heat, cooling the tissues and suit materials from which it escapes. The loss of pressure and the loss of warmth therefore reinforce one another, though neither proceeds uniformly across the body. Some of the vapor may freeze or condense on colder inner layers before it finds a route outside. The suit can briefly redistribute water rather than simply release it. A warm region near the torso may supply vapor that collects inside a shaded glove or across the visor. Later, sunlight could warm that deposit and send it back into the gas. These small cycles would continue as long as pressure and heat allowed, moving the body's moisture through an enclosure never designed to become a long-term, closed ecosystem. The outer thermal layers complicate this movement. They are designed to reduce rapid heating in sunlight and rapid cooling in darkness, protecting a living astronaut whose body and equipment produce heat. After death, metabolic heat ends, but the insulation remains. It slows some changes while allowing others to continue internally. A body exposed directly to vacuum begins losing surface moisture immediately. A body behind multiple suit layers can retain a warmer and wetter interior for longer. That delay does not preserve the body in its original state. It gives autolysis and microbial activity more time before drying and cold suppress them. By the time the suit loses most of its pressure, soft organs may already have changed substantially. Gas and fluid may have moved into places they did not occupy during life. The outer shape can remain constrained and recognizable, while a quieter transformation advances beneath the garment. If the suit was punctured during the fatal event, the pattern becomes still less uniform. Tissue near the opening faces rapid decompression, evaporation, and cooling, while areas deeper inside remain sheltered. A tear can become the main path by which moisture leaves, slowly drying the body from one region toward another. The wound in the suit is no longer only the cause of death. It becomes the feature that organizes everything happening afterward. With no observer and no possibility of repair, these changes can unfold almost invisibly. The suit may look undamaged from a distance. Its reflective layers still catch sunlight. National markings remain visible, and the helmet keeps its familiar shape. Yet internal pressure can be declining molecule by molecule. While moisture migrates, microbes consume the last favorable regions, and tissues cool into states where ordinary decay can no longer continue. Eventually, the active microbial phase weakens. Nutrients may remain abundant, but usable water and suitable temperature become harder to maintain. Some organisms die as their surroundings become too dry, too cold, or chemically hostile. Others enter dormant states within protected material. Enzymatic reactions slow for the same reason. Biological molecules may still be present, but without liquid water and thermal energy, they cannot interact at their earlier pace. The suit itself can hold small reserves of moisture after much of the body has begun drying. Absorbent fabrics, cooling garments, joints, and trapped pockets may contain ice or condensed water. This means the transition is gradual. One area can be dry while another remains frozen, and a warmer passage through sunlight may briefly release vapor that later freezes elsewhere. There is no single instant when the entire enclosure becomes empty. Over longer periods, the difference between an intact suit and a torn one narrows. Slow leaks continue. Temperature cycles work on seals and flexible materials. Tiny impacts may create new openings, while radiation gradually weakens exposed surfaces. These influences belong to the much longer story of erosion, but their earliest effect is simple. Every new path to vacuum makes it easier for gas and water to leave. What remains when the internal atmosphere has nearly disappeared is not the same body that first entered the suit. It may have undergone hours or days of enclosed change before vacuum fully took control. Some tissues have broken down, some fluids have moved into fabric, and some moisture has frozen along colder surfaces. The pressure garment has slowed the transformation, without preventing it, preserving not a person, but a sequence of intermediate states. This is why the suit cannot be treated as a minor detail in the fate of human remains. It determines whether early decomposition is cut short or given time to continue. It controls how gases escape, where water collects, how quickly heat is lost, and which tissues meet vacuum first. Two bodies following identical paths through space could develop very differently if one were exposed and the other remained enclosed. At last, however, the pressure inside approaches the emptiness outside. The remaining gases become too thin to support familiar chemistry, and moisture increasingly leaves the tissues themselves. The suit may still surround the body, but its small artificial atmosphere has faded. From this point, the most important material is no longer the gas trapped around the remains, but the water still held within them. Water once allowed every cell to function, carried heat and chemicals through the body, and gave soft tissue much of its form. After death, it continues to determine whether enzymes can react, whether microbes can grow, and whether tissue remains flexible or becomes dry and brittle. Once that water begins escaping into vacuum, the body enters a slower transformation that can resemble preservation, while quietly changing almost everything it leaves behind. More than half of a living human body is water, but that water is not held in one internal reservoir. It fills cells, moves through blood and lymph, surrounds proteins, cushions organs, lubricates joints, and occupies spaces too small to see. Some of it can move freely, while some is closely associated with biological structures. When pressure disappears, these different forms of water do not leave together. The surface responds quickly, but the interior must release its moisture through layers of tissue that were never designed to dry from the outside inward. At first, exposed water faces a pressure so low that it cannot remain liquid in the familiar way. Moisture on the eyes, mouth, airways, and damaged skin begins to evaporate or boil, even though the body is not hot. This change of state consumes energy. Each molecule that escapes carries heat away, cooling the material it leaves behind. The process, therefore, creates its own break. Rapid evaporation lowers the temperature, and the remaining water can begin to freeze. That combination seems contradictory, only because life on Earth usually separates boiling from freezing. In vacuum, pressure changes the rules. Liquid water can vaporize rapidly, lose heat, and leave a colder portion behind as ice. Once frozen, the ice does not need to melt before it can continue escaping. Molecules can pass directly from solid ice into vapor through sublimation, but this requires energy and can proceed much more slowly than the first loss from a wet surface. The body would not dry all at once. Skin, clothing, and the outer layers of tissue limit the path from the interior to space. Water deep within muscle or an organ must move toward a surface, pass through openings, or become vapor within connected spaces before it can leave. As the outer tissue dries or freezes, it may form a barrier that slows the release from beneath it. A body that appears dry on the outside could still contain ice and moisture much deeper within. Injuries and natural openings would become important routes. A torn suit and damaged skin expose internal tissue directly, while the mouth, nose, and airways provide paths from some cavities. The digestive tract and other enclosed spaces may retain moisture longer unless pressure changes open them to the exterior. The pattern of drying would reflect the body's condition at death, not a smooth and uniform retreat of water from every cell. This is why the phrase "freeze-dried in space" is useful but incomplete. Laboratory freeze-drying begins by freezing material, lowering the pressure, and carefully supplying enough heat for ice to sublimate without melting. The process is controlled so moisture can travel outward and be removed. Deep space supplies the low pressure, and it may supply cold, but it does not regulate the heat or create an efficient path through a human body. The result can resemble freeze-drying without matching the clean, predictable process used for food or medicine. An exposed body near a star may receive enough energy for sublimation to continue from illuminated surfaces. In shadow, the same body may cool until water loss becomes extremely slow. Rotation can alternate these conditions, warming one region and then another. The outer layers may pass repeatedly through periods of vapor release and near stillness, while the interior changes more gradually. Distance from the star, the angle of light, clothing, and the remains of a suit all shape the rate. As water leaves cells, their membranes collapse and their contents become concentrated. Salts that were dissolved in fluid remain behind. Proteins lose the surrounding water that helped maintain their working shape, and chemical reactions slow because molecules can no longer move and meet as easily. The tissue does not simply become a lighter version of itself. Its microscopic structure changes, often irreversibly, as shrinking and freezing pull once organized material out of its living arrangement. Soft organs contain large amounts of water and can lose volume as they dry. Muscle fibers contract and stiffen. Skin becomes less flexible and may draw tightly over underlying structures. The face and limbs can gradually take on a shrunken appearance, though swelling or damage from the earlier decompression may complicate that shape. A body held within a suit can be compressed by clothing and restraint layers while it dries, preserving folds and positions imposed by the equipment around it. Fat behaves differently from water. It does not boil away under the same conditions, and it can remain after water-rich tissue has shrunk. Over time, fats may oxidize, split into smaller molecules, or change texture depending on radiation, temperature, and the small amount of chemistry still possible. Their persistence means that dehydration alone does not reduce the body to bone. A complex mixture of dried proteins, fats, minerals, and residual water remains attached to the skeleton. Bone itself is not completely dry. Living bone contains water and organic material as well as mineral crystals. Some moisture occupies tiny pores, and collagen gives the structure part of its toughness. The outer soft tissues may dry long before water deep within bone escapes. If that water is eventually lost and the collagen is damaged, bone can become more brittle, even while its overall shape survives much longer than the organs around it. Dehydration changes the microbial story as well. Microorganisms need accessible water to grow and carry out metabolism. As tissues dry, the amount of water available to them falls, even if some molecules remain tightly bound within the material. Communities that were active soon after death become limited to the last protected moist regions. When those disappear, most growth stops, and decomposition loses one of its strongest early drivers. Stopping growth is not the same as sterilizing the body. Some bacteria and other microscopic life can tolerate drying, particularly when buried inside tissue or protected by salts and organic material. They may become dormant rather than die. Space exposure experiments have shown that shielding can allow certain microbes to survive vacuum far better than organisms left under direct solar radiation. A dried body might therefore preserve small pockets of viable life without allowing them to continue consuming it. Autolysis also slows as water becomes unavailable. Enzymes are physical molecules that require suitable surroundings to interact with their targets. Drying can distort them, trap them in place, or separate them from the material they would otherwise break down. The self-digestion that began soon after death can halt before it reaches completion, leaving partially altered organs fixed in a dried state. The timing of that halt is crucial. If an intact suit retained warmth and moisture for many hours, extensive internal change may have occurred before vacuum took control. If the body was exposed immediately, evaporation and cooling could suppress microbes and enzymes sooner. Both bodies might later appear mummified, yet their internal structures would record very different early histories. The final dry appearance cannot reveal the entire root that produced it. Cracks may develop as tissues shrink at different rates. Skin, muscle, fat, and connective tissue do not lose water in the same way, and repeated temperature changes add stress between them. A dry outer layer may split, exposing a still frozen region beneath. That opening provides a shorter route for vapor to escape, so drying can advance in uneven steps rather than as one continuous front. Any remaining clothing becomes part of this front. Fabric can wick moisture away from skin, spread it across a wider area, and then release it to the suit atmosphere or vacuum. Thick padding may shield ice and slow sublimation, while thin material exposed to sunlight can warm more readily. Metal rings and tools conduct heat into or away from nearby sections, creating small zones with their own histories. The human body and its equipment gradually become one connected thermal and drying system. The vapor that leaves does not form a lasting cloud around the remains. In near vacuum, molecules spread away, following their own paths until they strike the suit, the spacecraft, another object, or continue into space. Some may condense as frost on a nearby cold surface. If the body remains inside a damaged suit, Tiny ice deposits could appear along leak paths before later warming releases them again. Most of the water eventually becomes too dispersed to identify as something that once belonged to a person. There is something quietly strange in that dispersal. Water that moved through a living brain or carried oxygen in blood becomes an expanding population of ordinary molecules, indistinguishable from water, released by a spacecraft or comet. The body loses not only mass, but one of the materials that made coordinated life possible. What stays behind becomes increasingly mineral, fatty, and dry, while what leaves joins the environment without carrying a visible trace of its origin. Yet even very long exposure may not remove every molecule of water. Some is held strongly within minerals or molecular structures and requires more energy to escape. Deep interiors can remain shielded by layers that are poor conductors of heat. As drying continues, the easiest water leaves first, and each remaining portion can become more difficult to reach. The final stages may take far longer than the dramatic early boiling suggests. This slowing process helps explain how recognizable remains might persist. Without water, microbes cannot rapidly consume tissue, enzymes cannot continue normal reactions, and many forms of chemical change become limited. Dry skin and connective tissue can hold the skeleton together. The body may keep its overall outline even as its mass falls and its internal architecture collapses. To a distant observer, it could look preserved, but preservation here means that change has become slow, not that it has ended. No single estimate can say how long complete drying would take. A body turning near the sun, one sealed in reflective layers, and one drifting in cold darkness, receive different amounts of energy. The size and location of every opening change the route for vapor. Ice can remain stable in a shaded pocket, while tissue only centimeters away loses water steadily. Even the body's rotation may decide which surfaces are warmed often enough to continue sublimating. The same uncertainty extends to its final texture and appearance. A slowly dried body may retain more of its shape than one exposed to repeated warming and freezing. Fast surface loss can create a rigid outer layer that traps deeper ice, while gradual drying may shrink tissue more evenly. Collisions or bending at a brittle joint can break structures that would once have flexed. The result is not a universal space mummy, but a record of pressure, shielding, heat, and time. As the accessible water disappears, the rapid post-mortem processes finally give way to much slower ones. Microbial growth fades, self-digestion stalls, and the body no longer changes on the familiar timetable of days and weeks. What remains is still vulnerable, but its future is measured less by decay than by the energy arriving from its surroundings and the material slowly leaving or breaking apart. That energy is never distributed evenly. One side may face a star, while another radiates into darkness. A slow rotation can share the heating. A fixed orientation can preserve an extreme contrast. An intact suit can reflect much of the light, while exposed dark material absorbs more. The vacuum itself does not tell the body whether to freeze or warm. It only removes the air that would have made temperature easier to understand. Water loss has therefore carried the story toward a deeper problem. Boiling, freezing, and sublimation all depend not only on pressure, but on the movement of heat. When evaporation cools the tissue, the process slows unless new energy arrives. When ice lies in darkness, it can remain for an extraordinary time. When sunlight warms it, molecules escape more readily. The body's drying rate is ultimately a thermal history written across every surface. By the time the remains are largely dehydrated, the simple image of cold space has become impossible to trust. Space provides almost no air to measure, touch, or carry heat, and the temperature of an object depends on what it absorbs and what it radiates away. The water can leave only as quickly as heat allows it to change state, which means the fate of the dried body is now tied to a question space never answers with one number: its temperature. Temperature is easy to imagine on Earth because air is always touching us. Warm air transfers energy to the skin, cold air carries energy away, and moving wind makes the exchange faster. A thermometer reaches a balance with the surrounding gas and gives the environment a familiar number. In deep space, there may be so few nearby particles that this kind of measurement loses much of its meaning. The vacuum is not a cold wind waiting to strike the body. There is almost nothing there to touch it at all. Heat can still move through emptiness, but it travels mainly as radiation. Every object above absolute zero emits electromagnetic energy, much of it at wavelengths human eyes cannot see. A warm body radiates energy outward. A nearby star sends energy back in the form of visible light, infrared, and other radiation. The body's temperature changes according to the balance between what it absorbs and what it releases. This is why the body would not freeze the moment it met vacuum. It begins with stored thermal energy in its tissues, clothing, and equipment. Without air, there is no convection to strip that heat away. Evaporating water cools exposed surfaces, and heat conducts from warmer regions into cooler ones. But the complete loss must still take time. The body is not suddenly placed at the temperature of some imaginary substance called space. It must cool by sending its own energy away. At first, a warm surface radiates more strongly than a cool one. As its temperature falls, the rate of radiative loss falls sharply as well. Cooling therefore slows as it proceeds. The early drop may be noticeable, especially while water is evaporating, but the final approach toward a very cold equilibrium can be extraordinarily gradual. The body never reaches a perfect endpoint in a single step. Near Earth, sunlight is the largest external source of heat. A surface facing the sun receives a steady stream of energy, while a surface facing away radiates toward the dark sky. An exposed body could therefore develop a warm, illuminated side and a much colder, shaded side. Heat conducted through tissue would reduce the difference, but drying, clothing, and the insulating layers of a suit can slow that internal transfer. The contrast would depend on color and material. Dark surfaces usually absorb more incoming sunlight, while reflective outer layers reject much of it. Spacesuits use bright, carefully chosen materials partly to manage this balance. Once the suit is damaged or aged, patches of exposed fabric, skin, metal, and visor no longer behave alike. Two areas only centimeters apart can absorb and emit energy at different rates. The word hot also becomes deceptive here. A surface receiving direct sunlight may reach a high temperature without the vacuum around it containing much heat. Turn that surface away, and the incoming energy drops immediately, while radiation continues outward. Nothing in the surrounding air softens the transition, because there is no meaningful surrounding air. Temperature belongs to the object and its energy balance, not to an invisible ocean filling the space around it. Rotation can share the incoming energy across the remains. A slowly tumbling body exposes the torso, back, helmet, and limbs to sunlight in sequence, giving each region time to warm and cool. Faster rotation can smooth some of the contrast, while a body locked in one orientation may keep the same side illuminated for long periods. The motion inherited from the accident can therefore shape the thermal history for years. An orbit adds another rhythm. A body circling Earth may pass repeatedly through sunlight and planetary shadow. During each illuminated portion, it absorbs direct sunlight, reflected light from Earth, and infrared energy emitted by the planet. In eclipse, those inputs change, and the body begins radiating more energy than it receives. The cycle repeats every orbit, expanding and contracting materials, while water freezes, sublimes, or migrates through the remains. Repeated heating and cooling can be more damaging than a stable cold, Skin, bone, fabric, plastics, and metal do not expand by identical amounts when warmed. Where they are connected, small stresses appear. Over many cycles, dry tissue can crack, coatings can separate, and seals can weaken. A joint fixed in one position may become brittle along the lines where sunlight and shadow repeatedly divide it. This does not mean the body alternates cleanly between being frozen and thawed. The interior responds more slowly than the surface. A visor can warm while ice remains inside the torso. A dark patch can lose frost while tissue beneath a reflective layer stays cold. Thermal change moves through the body by conduction, and dried biological material is not an efficient conductor. Different depths can occupy different temperature histories at the same moment. If ice does warm enough to sublime, the escaping vapor carries energy away and cools the region again. This creates another temporary resistance to warming. Incoming sunlight may be spent changing ice into vapor, rather than raising the tissue's temperature. Once most accessible ice is gone, the same surface can warm differently, because that cooling path has disappeared. The body's thermal behavior changes as its composition changes. Farther from the sun, the incoming energy weakens. At the distance of Mars, it is already smaller than near Earth, and beyond the outer planets it becomes only a faint contribution. A body drifting away from the solar system would cool toward a balance set by distant starlight, the weak glow of interstellar surroundings, and the radiation left from the early universe. The transition is continuous. There is no boundary at which warm space suddenly becomes cold space. The cosmic microwave background is often given a temperature of about 2.7 Kelvin, only a few degrees above absolute zero. It fills the universe with faint radiation and provides a useful description of the deepest background. Yet this number does not mean every object in interstellar space instantly becomes 2.7 Kelvin. Stars, dust, nearby planets, internal radioactivity, collisions, and the object's own stored heat all affect the balance. Reaching any extremely low temperature also becomes slower as the remaining heat decreases. A human body carries very little long-term internal heat once metabolism has stopped, but not every component becomes thermally inactive. Some radioactive isotopes naturally present in tissue and bone release tiny amounts of energy, though far too little to keep the remains warm in the ordinary sense. Chemical reactions can produce small local changes while they continue. Compared with sunlight near a star, these sources are negligible. But in very cold darkness, even weak inputs belong to the final equilibrium. The suit can delay that equilibrium without choosing it. Its outer layers reduce the exchange of radiation, and gaps between layers limit conduction. This insulation was designed to protect a living astronaut, whose body and equipment continually created heat. Around human remains, it slows both warming and cooling. A shaded body inside an intact suit may retain internal heat longer, while the same insulation can also slow the arrival of sunlight into deeper material. Metal components create exceptions. Bearings, connectors, tools, and backpack structures can conduct heat efficiently between places that fabric leaves isolated. A sunlit metal ring may warm a nearby section of the suit, while a shaded piece radiates energy away and cools what touches it. These pathways form a complicated thermal map that changes as the body rotates and the materials age. The visor has its own role. Transparent layers emit some wavelengths, reflect others, and radiate heat from their surfaces. Sunlight passing through can warm darker material inside the helmet, while coatings reduce ultraviolet and infrared exposure. Frost or residue changes those optical properties, sometimes making the visor absorb more or reflect differently than it did when clean. The enclosure gradually loses the predictable behavior it had when engineers could monitor it. An unprotected body would be simpler only in comparison. Skin, dried tissue, exposed bone, and remaining clothing still absorb and emit radiation differently. The shape of the body creates permanent shadows beneath arms, behind the head, and within folds. Some of these sheltered regions may preserve ice much longer than surfaces that see the sun. Even a bare body carries its own landscape of light and darkness. Near other worlds, the situation changes again. A giant planet can emit infrared energy and reflect sunlight, while its shadow creates long, cold intervals. A small moon may offer reflected light from a nearby planet. A thin atmosphere can introduce limited collisions with gas particles, and a dense atmosphere would end the deep space conditions entirely. The body's temperature is always a statement about location, orientation, and time. Approaching a star would reverse the trend. Incoming radiation rises rapidly as distance decreases. Long before physical contact, exposed materials can warm enough to release remaining water and volatile chemicals. Fabrics weaken, organic material darkens or chars, and eventually, the remains can be destroyed by heat. A path toward the inner solar system therefore produces a fate entirely different from a path into interstellar night. Yet an orbit can remain stable enough that neither extreme arrives. The body may circle a star or planet for years, repeatedly passing through a limited range of temperatures. In that case, gradual thermal cycling matters more than a final freeze or burn. Small changes accumulate. Another crack opens. Another pocket of ice escapes. Another seal loses flexibility. The absence of dramatic motion does not mean the material has stopped evolving. Cold can preserve form by slowing chemical reactions, but it cannot restore what was lost during the warm hours after death. Autolysis and microbial activity may already have altered soft organs before the body cooled. Ice crystals may have damaged cell structure. Later, freezing simply holds that changed arrangement in place. A face that remains recognizable after years in darkness is not biologically untouched. It is a record paused after several earlier transformations. Warmth can briefly restart processes only where water and suitable chemistry remain. If a frozen pocket inside a suit thaws during a close passage to a star, microbes or enzymes may become active again for a time. As water evaporates, the window closes. The body can move through repeated phases of activity and stillness without ever returning to the continuous decay expected on Earth. These variations make any single predicted temperature misleading. Saying that the body would be frozen ignores sunlight and insulation. Saying it would burn ignores shadow and distance. Even quoting the temperature of the cosmic background describes only one source of radiation in an idealized deep void. The real remains find their temperature by continuously negotiating with every source they can see and every surface through which they can lose energy. Eventually, if the body travels far from bright stars and remains there, it becomes extremely cold. Most accessible water is frozen or gone. Molecular motion slows, and ordinary chemistry becomes rare. The outer shape may persist through a period far longer than a human lifetime. But cold is not a shield against every influence. The object remains exposed to light and high-energy particles that do not require warmth to cause damage. Some of that radiation arrives as ultraviolet light from stars, carrying enough energy to break chemical bonds near exposed surfaces. Other particles cross the body from distant events in the galaxy, leaving trails of ionization through tissue, bone, and suit material. Heat tells us how quickly molecules move. It does not determine whether an energetic photon or particle can strike them. A frozen body can be chemically altered even while almost every thermal process is slowed. The long future of the remains is therefore not secured by reaching a cold equilibrium. Temperature can slow decay, retain ice, and make tissue brittle, but it cannot make the body invisible to the universe. Whether warmed by a nearby star or cooled in interstellar darkness, it continues to receive energy in forms more penetrating than heat. Once the body reaches its changing thermal balance, another influence continues whether it is hot or cold, lit or dark. Radiation. The word covers several different things. Ordinary visible light is radiation, as is the infrared energy that warms a surface. Ultraviolet light carries more energy, while X-rays and gamma rays can penetrate farther and alter atoms within material. Space also contains fast-moving protons, electrons, and the stripped nuclei of atoms arriving from the Sun, planetary radiation belts, and distant events across the galaxy. Their effects cannot be reduced to one beam or one steady dose. For a living astronaut, the danger of ionizing radiation is measured through the injuries it can cause to active cells. DNA can break, cell machinery can fail, and damaged tissue may later develop disease. A dead body cannot develop cancer or radiation sickness, but the physical damage still occurs. The difference is that nothing repairs it. Molecules are broken or changed, and each alteration remains available for the next exposure to build upon. Sunlight begins working at the outer surface. Ultraviolet photons are energetic enough to disrupt chemical bonds in skin, fabric, plastics, coatings, and pigments. The effect is familiar in a mild form on Earth, where sunlight fades cloth and weakens materials left outdoors. In space, there is no atmosphere to remove the most energetic parts of the solar ultraviolet spectrum, although a visor or suit layer may still provide shielding. An exposed face or hand would receive this light directly whenever it turned toward the star. Dried tissue could darken in some places, bleach in others, and develop a brittle surface as proteins and fats are altered. These changes would not sweep through the whole body at once. Ultraviolet light is most effective near the surface, so folds, clothing, the back of the body, and regions beneath the suit remain protected until their covering fails or the body changes orientation. Rotation writes the exposure in layers of time. A tumbling body shares sunlight across different surfaces, while one held in a stable orientation can leave the same side illuminated for years. A deep crease may remain sheltered even when the surrounding tissue has been heavily altered. The resulting pattern would reflect the path through light, just as drying reflected the paths through which water escaped. The suit's outer garment delays some of this process, but it also becomes part of it. Reflective layers and protective fabrics are designed to survive the limited duration of missions and repeated spacewalks. They reduce ultraviolet exposure, manage heat, and protect the pressure bladder beneath. They are not designed to remain unattended under sunlight for centuries. Chemical bonds in polymers slowly break, colors change, and materials lose flexibility. As the outer surface weakens, tiny cracks can expose deeper layers that had received far less light. A coating that once reflected solar energy may begin absorbing more after it is damaged or contaminated, changing the local temperature as well as the radiation exposure beneath it. Radiation and heat, therefore, do not act as separate stories. Each can alter the material in a way that changes how the other is received. Ultraviolet damage also changes how easily the remains can be eroded later. A flexible fabric can absorb a small impact, while the same fabric, after long irradiation, may split. Skin and connective tissue that once held dried structures together become less resistant as molecular chains are cut. The radiation does not need to remove a visible piece immediately. It prepares the material to lose pieces when another force arrives. More penetrating radiation follows a different path. Galactic cosmic rays include protons and heavier atomic nuclei, moving at enormous speeds, many close to the speed of light. They are sparse compared with sunlight, but each particle can carry enough energy to pass through a suit and into the body. Along its route, it knocks electrons away from atoms, leaving a narrow trail of ionized material. Those trails may cross skin, muscle, bone, or the remains of an organ without producing a mark visible from outside. At molecular scale, however, they can break DNA strands, alter proteins, and change minerals. A heavy cosmic ray nucleus can deposit energy densely along its path, while interactions with atoms in the suit or body may produce secondary particles that travel away from the original collision. Shielding can reduce some exposures, but it cannot make a thin garment completely silent to such particles. During life, damage to DNA would matter because cells read and copy that information. After death, DNA has a different significance. It is a chemical record of the person and a material that future investigators might hope to recover. Radiation, water loss, temperature changes, and time all fragment that record. The body may remain recognizable long after its genetic material has become difficult or impossible to reconstruct in complete sequences. The loss would be uneven. Bone and teeth can protect some biological molecules better than exposed soft tissue. The interior of a thick bone receives less ultraviolet light, although penetrating particles can still cross it. A suit, clothing, and dried outer tissue add further shielding. Tiny fragments of DNA may survive in sheltered places after exposed regions have been chemically transformed beyond recognition. Proteins follow the same broad pattern, without carrying the same information. Collagen gives skin, tendons, and bone much of their strength. Radiation can break its long molecular chains or create new links between them, changing toughness and flexibility. Other proteins lose structure and become easier to fragment. The remains may keep their shape for a time, while the material responsible for that shape is becoming progressively weaker. Fats can undergo radiation-driven chemical changes as well. High-energy exposure can create reactive fragments, and any available oxygen may support further oxidation. In a thoroughly dried body, the chemistry is limited, but it does not vanish. Small reactions continue near exposed surfaces and along particle tracks, producing volatile molecules that can eventually escape into vacuum and leaving heavier residues behind. Bone appears durable because its mineral framework survives conditions that destroy soft tissue. Even so, bone is a composite of mineral and collagen rather than a solid block of stone. Damage to the organic part makes it more brittle. Radiation can also disturb atoms in the mineral structure. These changes accumulate slowly, and the skeleton may look intact long after its resistance to cracking has declined. The dose depends strongly on location. Near Earth, the planet's magnetic field deflects many charged particles, but also traps energetic particles in radiation belts. Low orbits receive some protection from Earth itself, which blocks part of the sky. Farther out, the body loses that shelter and encounters the broader solar and galactic environment. Near a strongly magnetized planet, trapped radiation can become far more intense than the background between worlds. Solar activity makes the environment change with time. Most days bring a steady flow of particles from the sun, but eruptions can launch much larger clouds of energetic protons and electrons. A body in the wrong place during one of these events may receive a concentrated exposure over hours or days. Farther from the sun, the cloud spreads, yet major events can still influence a large region of the solar system. Galactic cosmic rays behave differently. They arrive from many directions and are present even when the sun is quiet. Solar magnetic activity can reduce how many lower-energy galactic particles enter the inner solar system, creating a relationship in which one radiation source rises as another is partly suppressed. For drifting remains, this means the long-term dose is not a smooth line, but a history of changing environments. Deep interstellar space is not free of radiation. The direct ultraviolet light from the sun fades with distance, but cosmic rays continue crossing the galaxy. Other stars contribute light, and rare energetic events can briefly alter local conditions. The body may become colder and darker without ever becoming fully shielded. Its thermal story can settle while its molecular damage continues. There is no useful date at which radiation suddenly destroys the body. The rates depend on shielding, orientation, location, solar activity, and the material being considered. A surface coating can fail while bone remains strong. DNA may fragment long before the outline of the body changes. A suit can keep its recognizable form, even as individual fibers lose much of their original strength. This separation between appearance and structure is one of the strangest parts of the journey. Human eyes recognize shape, not molecular integrity. A helmet, folded arm, or profile behind a visor can still suggest a person, while the organic record beneath has become a patchwork of broken chains and altered compounds. Radiation does not need to erase the silhouette in order to erase much of what once made the material biologically distinct. Given enough time, even the silhouette becomes vulnerable. Ultraviolet exposure weakens the surface. Ionizing particles cross the interior, and thermal cycles open cracks along stressed boundaries. A visor may cloud and craze. Fabric can lose strength around joints. Dried tissue can separate from bone. The body is being prepared for physical fragmentation, even if radiation alone removes very little mass. Some molecules released by this damage escape as gas. Others remain as dark residues or tiny particles attached to the surface. The changes can alter color and texture, but there is no universal path from pale tissue to one final appearance. Light exposure may bleach one material and darken another. A protected side can retain an earlier color, while the illuminated side becomes chemically older. The pace is almost impossible to feel on a human scale. During a lifetime, the remains might look nearly unchanged from a distance. Across thousands or millions of years, small changes cease to be small. Countless ultraviolet photons strike exposed surfaces, and rare high-energy particles accumulate tracks through every region. The body experiences no single fatal dose. Because it is already dead, it experiences an open-ended total. Cold cannot stop this accumulation. A frozen molecule is moving less, but an energetic photon can still be absorbed, and a cosmic ray particle can still ionize the atoms it crosses. Some follow-on reactions slow at low temperature, yet the initial break remains. When a later period of sunlight warms the material, trapped reactive fragments may gain enough movement to continue their chemistry. Damage can be created in darkness and expressed during warmth. Nor can the suit provide permanent protection. More material blocks more radiation, but high-energy cosmic rays can penetrate ordinary spacecraft structures, and collisions inside shielding can generate secondary particles. A suit is thin because an astronaut must move in it. It can screen much of the ultraviolet light and some lower-energy particles, but it was never a fortress against the full galactic environment. By weakening the suit, radiation also changes the body's exposure to everything else. New tears let remaining gases and vapor escape. Broken outer layers alter heating. A small impact that once would have left only a mark can open a brittle fabric and scatter fragments. The long effects of light and particles become visible mainly when the damaged material is finally asked to resist a physical force. Space contains many such forces, even where it appears empty. Dust grains cross planetary systems, tiny meteoroids orbit stars, and fragments of old collisions travel at speeds that turn microscopic objects into projectiles. Individual encounters may be separated by long, quiet intervals, but the weakened remains have no way to heal between them. Radiation has therefore changed the question from how long the body can resist chemistry to how long its structure can resist being struck. It has faded pigments, fragmented molecules, weakened fibers, and made dried tissue more brittle, all without the dramatic destruction that would reveal the process from afar. Once radiation has prepared those materials to fracture, the smallest pieces of matter moving through space can begin doing what light alone rarely does: carrying them away. Space appears empty because the distances between visible objects are enormous. But emptiness is not the same as perfect absence. Dust is released by comets, chipped from asteroids, thrown from planetary surfaces, and created when larger bodies collide. Near Earth, fragments of rockets, spacecraft, paint, and other human objects add an artificial population. Most particles are too small to see, yet their speed can make their size misleading. On Earth, a grain of dust settles, softly, because air slows it. In orbit or interplanetary space, two objects can approach one another from very different directions, while each moves at many kilometers per second. The energy of an impact depends strongly on that relative speed. A particle smaller than a grain of sand can strike with enough force to pit metal, cut fibers, or vaporize part of itself and the surface it hits. The collision does not resemble a slow puncture. At hypervelocity, pressure rises at the point of contact faster than the surrounding material can respond. The projectile can shatter or melt, and a tiny crater forms as material is compressed and thrown outward. Some of the target becomes ejecta, leaving as droplets, vapor, or fragments. The amount removed in one event may be microscopic, but it is genuinely gone. Spacesuits are built with outer layers that reduce this risk during a spacewalk. Their fabrics spread and absorb energy before a small projectile can reach the pressure bladder. Engineers test suit materials against high-speed impacts, because a hole that reaches the bladder can allow air to escape. Those protections are designed for a limited mission, with the suit inspected, repaired, and replaced when necessary. A drifting suit receives no such care. Radiation and temperature cycling gradually make those protective layers less reliable. Fibers lose strength, coatings crack, and joints become brittle. A particle that might once have damaged only the outside can penetrate farther after centuries of weakening. The history of the suit therefore changes the meaning of every later collision. The same impactor can leave a shallow mark early and open a deeper wound much later. Once a particle passes through the outer garment, it may cross empty space inside the suit before striking dried tissue, bone, metal, or another layer of fabric. It can create more than one hole along its path. Fragments from the first impact may spread into a small cone, so a single incoming grain produces several smaller strikes inside. The body and the suit become both targets and sources of new debris. An exposed body offers less resistance. Dry skin and connective tissue can chip at the surface, especially after radiation has weakened them. Bone may develop a tiny crater or fracture around an existing flaw. If the impact reaches a joint already made brittle by dehydration and thermal cycling, a larger piece can separate. The body is not worn down evenly. It accumulates isolated points of damage that sometimes connect. Most encounters would leave marks too small to change the silhouette. A new pit appears on a visor. A thread is cut. A speck of dried tissue leaves the hand or face and enters its own path through space. From a distance, the astronaut can still look whole, while close inspection would reveal a surface slowly becoming scarred by events separated by years or longer. Frequency matters as much as force. A region filled with orbital debris or dense dust presents more opportunities for impact than the quiet space between stars. Low Earth orbit contains many human-made fragments moving on crossing paths, while interplanetary space contains natural dust orbiting the Sun. Far beyond the planetary system, the density may be much lower, but the body can spend an immensely longer time there. Human timescales encourage the wrong intuition. A rare event seems unimportant if nothing happens during an hour, a year, or even a century. Over millions of years, a small probability repeated without end becomes part of the material's history. The body does not need to enter a visible dust cloud to be altered. Long, quiet intervals can separate one meaningful impact from another. There is no guarantee that those impacts remain small. A pebble, fragment of debris, or larger meteoroid could break the suit and body apart in one collision if their paths happen to cross. Such an encounter may be unlikely in an empty region, but its consequence would be severe. The title of slow erosion describes the most gradual path, not a rule protecting the remains from sudden destruction. Location changes both the number and direction of possible projectiles. Near a comet, fresh dust can stream away from the warming surface. Within a ring system, countless particles share related orbits but still collide as those orbits intersect. Close to a moon, material thrown upward by other impacts may return along ballistic paths. Near an active spacecraft route, artificial debris can dominate the risk. In low Earth orbit, another erosive influence joins the impacts. The upper atmosphere is extremely thin, yet it contains atomic oxygen that can react strongly with exposed organic materials and some spacecraft surfaces. Each individual encounter is tiny, but an object moving through the atmosphere experiences a continuous stream. Fabric, polymers, and dried tissue would be affected differently from a body in true interplanetary vacuum. That faint atmosphere also creates drag. It removes orbital energy, slowly lowering the path until denser air causes re-entry. If the remains stayed low enough, atmospheric heating would eventually overwhelm the long process of micrometeoroid erosion. They might burn, fragment, and fall, rather than remain in space. The slow cosmic future is possible only on an orbit or escape path that avoids this return. Farther from Earth, human-made debris becomes less important and natural micrometeoroids dominate. Their speeds and directions reflect orbits around the Sun, so the body's own motion changes the relative impact. Moving into a stream of particles produces a different hazard from traveling alongside it. The surface facing forward along the path may collect more damage, much as the front of a vehicle receives more rain. A spinning body shares that exposure across several surfaces. One that maintains a stable orientation may develop a leading side marked by more craters and a trailing side that remains comparatively sheltered. Suit folds, the backpack, and the body itself cast physical shields against some directions. Damage maps the geometry of motion even when no observer is present to read it. Some particles do not remove material. They embed themselves. A micrometeoroid may melt or fragment on impact and leave part of its substance inside the crater. Over time, the remains can collect atoms and minerals that came from asteroids, comets, old spacecraft, or distant dust. The surface loses pieces of human material while gaining pieces of the environment, making the boundary between body and space less chemically clear. Larger impacts produce clouds of fragments that begin with similar positions but slightly different velocities. Those differences are enough to separate them gradually. A chip from the visor, a fiber from the suit, and a piece of bone may travel near one another for a time before gravity and later encounters pull their paths apart. Fragmentation does not make the material disappear. It changes one body into many smaller objects. Each fragment then presents a new surface to vacuum, light, and radiation. Material that was protected inside bone or beneath fabric becomes exposed. Remaining ice can sublime. Organic molecules can be altered by ultraviolet light, and further impacts can break the pieces again. Physical erosion accelerates other processes by continually uncovering regions that had escaped them. Size also changes the influence of radiation pressure, the gentle push delivered by light. For a human body, this force is weak compared with gravity, though over time it can modify a path slightly. For a tiny, detached grain, the ratio of surface area to mass is much larger, so sunlight can affect its orbit more strongly. The smaller the body becomes, the less faithfully its fragments follow the original route. Electric charge can add another difference. Ultraviolet light and surrounding plasma can cause exposed surfaces and dust grains to gain or lose electrons. Large remains are influenced only slightly. but microscopic particles can respond to electric and magnetic fields. A fragment released from the suit may therefore leave not only because of the impact that created it, but because forces almost irrelevant to the intact body become important at its new size. This gradual sorting spreads the remains across space. Heavy pieces may stay near the original orbit, while fine dust is more easily shifted. Some particles may strike a planet or moon, others may be swept inward toward a star, and still others can continue outward. There is no moment when the human material becomes nothing. It is redistributed until its pieces no longer form a recognizable whole. The suit can prolong that unity by holding fragments even after they break from the body. A loose chip may remain trapped between layers or inside the pressure garment. Torn fabric can act like a bag around brittle tissue, keeping pieces together while allowing vapor and dust to escape. Only when openings widen or the suit itself fragments do those protected pieces join independent paths. The visor and rigid torso can survive impacts differently from fabric. A small crater in a transparent helmet may remain localized, while a larger or repeated strike can create cracks that spread across the shell. Metal rings may resist penetration but release high-speed flakes from the inner surface. A structure that appears protective can turn an incoming particle into a wider spray of secondary fragments. No calculation can provide a universal erosion time without knowing the trajectory. Engineers estimate impact risk for spacecraft by modeling the local particle environment, the area and orientation of the target, the duration of exposure, and the strength of shielding. The same variables would be needed here, except the duration could extend far beyond any designed mission, and the materials would continue weakening as the estimate unfolded. In a quiet interstellar region, the remains might experience very little visible erosion for an extraordinary span. Interstellar dust exists, but it is sparse. A body moving slowly relative to the surrounding material would suffer gentler encounters than one traveling rapidly through it. The fact that the space is not perfectly empty does not imply a constant sandstorm. It means that silence contains occasional collisions. If the body traveled at a large fraction of the speed of light, even thin gas and tiny dust grains would become an extreme hazard. But an untethered astronaut begins with nothing close to such a velocity. It keeps the speed inherited from its spacecraft and gravitational encounters. Ordinary orbital and escape speeds are enough to make small impacts damaging without turning every isolated atom into a catastrophic projectile. Across immense time, the distinction between erosion and collision becomes a matter of scale. One atom changes chemistry. One grain makes a crater. One pebble breaks a structure, and one large object ends the recognizable form completely. The body's surface records whichever encounters its path permits. Space does not promise slow destruction. It only offers a very wide range of waiting times. That range makes the trajectory central to everything that follows. A body near Earth may encounter debris and atmosphere. One near a comet may cross dust streams, and one escaping the solar system may enter a far quieter environment. The same remains can be rapidly destroyed, slowly worn away, or almost untouched depending on where gravity carries them. The erosion of dust, therefore, cannot be separated from motion. The particles are not simply flying through a fixed scene toward a body suspended at its center. Both the remains and the potential impactors follow paths shaped by gravity, and their chances of meeting come from how those paths cross. To understand whether the next collision arrives tomorrow or after 1,000,000 years, we have to stop treating the body as still and follow the path gravity has given it. Nothing released into space simply stays where it was left. At the moment an astronaut loses contact with a spacecraft, the body already has a position and a velocity inherited from that vehicle. If the separation is gentle, both continue along nearly the same route. They may appear to drift apart slowly, yet together they are moving around a planet, around the Sun, or outward through the solar system, at speeds far greater than the small motion between them suggests. This is the central idea of an orbit. Gravity pulls the body inward, while its sideways motion continually carries it past the object below. It falls without reaching the surface because the surface curves away at the same time. The body needs no engine to keep moving along this path. In a near vacuum, it continues with almost no resistance, guided by gravity and whatever small forces act upon it. A push that looks weak can still matter. The air escaping from a suit, the motion of a crewmate, or the release from a hatch can change velocity by only a small amount. Yet that difference creates a new orbit. The body may move ahead of the spacecraft, fall behind it, rise to a slightly higher path, or descend toward a lower one. It does not travel in a straight line away from the vehicle, simply because the gap between them grows. If the accident occurs around Earth, altitude becomes one of the strongest clues to the long-term fate. In a low orbit, traces of atmosphere remain. Each passage creates a little drag, removing orbital energy and lowering the path. As the body descends, the air becomes denser, drag grows, and the final fall accelerates. Solar activity can expand the upper atmosphere and shorten a lifetime that might otherwise have been much longer. Re-entry would replace the slow, deep space processes with a violent thermal event. The body and suit would meet increasingly dense air at orbital speed, compressing and heating the gas ahead of them. Fabrics would tear or burn, biological material would char, and the remains would likely fragment. Some dense pieces might survive to lower altitudes, but the recognizable astronaut would almost certainly not reach the ground intact. Higher Earth orbits can persist far longer. With less atmospheric drag, a body might circle for centuries or more, sharing the region with satellites and debris. The path would be disturbed slightly by Earth's uneven gravity, the pull of the Moon and Sun, and pressure from sunlight. These influences may alter orientation and orbital shape without immediately ending the journey. An object in Earth orbit also passes repeatedly through the same broad environments. It may cross planetary shadow, encounter changing radiation, and return to regions where debris paths intersect. The body's previous stories of heating, radiation, and impact become periodic rather than random. Every orbit repeats the geometry, though the details slowly shift. A collision with a satellite or large fragment would end that regularity. The chance may be small, but the orbital lifetime can be long. If a major impact occurs, both objects can break into new debris, each piece receiving a different velocity. The body would no longer have one orbit, but a family of related paths spreading around Earth. Leaving Earth's orbit requires more than drifting away from a spacecraft. The body must already have enough energy to escape the planet's gravitational hold, usually because the spacecraft carrying it was on a departure trajectory. If released during a journey to the Moon, Mars, or another destination, the body continues along a path close to the planned route until small differences and later gravitational encounters separate it. Escaping Earth does not usually mean escaping the Sun. Once outside Earth's immediate influence, the body is still moving through the Sun's gravity and will normally follow its own heliocentric orbit. It may circle between the inner and outer solar system, cross the orbit of a planet, or remain on a path similar to the spacecraft from which it came. The Sun becomes the main focus of the motion, even when it is only a bright point in the distance. The shape of that solar orbit determines temperature and radiation. A path that approaches the Sun exposes the remains to increasing heat and ultraviolet light, perhaps destroying them during repeated close passes. An orbit that stays beyond the giant planets remains colder and encounters a different dust environment. The body carries no destination of its own. Its physics inherits one from the trajectory. Planetary encounters can rewrite that future. If the body passes close enough to a planet or moon, Gravity bends its route. Depending on the direction of approach, the encounter can add or remove energy relative to the Sun, just as planned gravity assists redirect spacecraft. A small difference in timing can separate a harmless, distant passage from capture, impact, or ejection onto a much wider orbit. Capture without propulsion is difficult, because energy must be exchanged, but it can occur through interactions involving an atmosphere, a moon, or a complex multi-body encounter. More often, a close flyby simply changes speed and direction. The body may leave the encounter heading toward a new region that it would never have reached along its earlier path. An impact with a planet or moon creates another range of endings. A thick atmosphere can heat and fragment the remains before they reach the surface. A thin atmosphere offers less braking, allowing a high-speed impact. An airless moon provides no gradual entry at all. The body strikes the ground at the speed set by gravity and its approach, breaking suit, bone, and equipment in a single event. If the remains land gently enough on a small body, the long environmental story changes again. They are no longer tumbling through open space but lying on a surface with gravity, dust, extreme day-night cycles, and local radiation. Ejecta from later impacts can bury or expose them. A place that seems like a final resting point may remain geologically active on a very slow scale. Falling into a gas giant offers no solid surface. Atmospheric entry becomes deeper and hotter as pressure rises, with winds and chemistry pulling material apart. Near the Sun, temperatures eventually vaporize organic matter and damage even the mineral skeleton. A black hole or neutron star could provide far more extreme outcomes, but an ordinary human trajectory would be extraordinarily unlikely to encounter one. Ejection from the solar system is possible only if the body begins with enough speed or gains energy through a favorable planetary encounter. It then follows an open path relative to the Sun rather than returning in an ellipse. Even so, leaving the planets behind is not the same as immediately leaving every part of the solar system. The distant Oort cloud may extend tens of thousands of times farther from the Sun than Earth. The voyagers show the scale. They have crossed the boundary where the solar wind yields to interstellar space. Yet, they will spend many thousands of years traveling through the Sun's distant domain before passing beyond the Oort cloud. A body on a similar escape path would cool, darken, and encounter sparse interstellar material while the solar system slowly receded behind it. There would be no frozen background of stars waiting in fixed positions. The Sun moves through the Milky Way. Other stars follow their own galactic paths, and the escaped body joins that larger motion. It does not aim at the constellation it appears to face from Earth, because the pattern will change long before it arrives. Its route is a curve through the gravitational field of the galaxy. A close stellar encounter is possible but unlikely. Stars are separated by enormous distances, and a human body presents a tiny target. It may pass light years from every star for millions of years. Gravitational pulls from distant stars and the galaxy still alter the path gently, while rare closer passages could bend it more noticeably. If the body did enter another planetary system, its speed might be too high for capture. It could pass through, on an open trajectory, briefly receiving stronger light and heat, before returning to interstellar darkness. A direct collision with a planet, moon, asteroid, or star would require an extraordinary alignment. Most of space is not occupied by destinations. Small non-gravitational forces accumulate as well. Sunlight exerts pressure, and uneven thermal radiation can produce minute changes in motion. Gas or water vapor escaping from one side of a suit creates a tiny thrust. Impacts add small impulses. For a full body, these effects are weak, but over long periods, they can shift timing enough to change a later planetary encounter. Fragmentation magnifies those differences. Once the remains break into pieces, Each fragment has its own area, mass, rotation, and response to light. Fine dust can be pushed more readily than bone or metal. A cluster that began together spreads into a long stream along the orbit, and later, gravitational encounters sort it further. The question of where the body goes eventually becomes many questions about where its material goes. The body's rotation has its own history separate from the orbit. A small push can start a tumble that continues in vacuum. Escaping gas, impacts, and uneven heating can slowly change that spin. Rotation controls which side faces sunlight, and incoming dust, connecting motion directly to preservation. There is no guarantee that one side remains protected forever. Long-term orbits can also become difficult to predict with perfect precision. Tiny uncertainties in the initial release grow as the path experiences repeated encounters and perturbations. A close pass by a planet can amplify a difference too small to notice years earlier. We may describe categories of fate, but without exact starting conditions, there is no single map for the body. This uncertainty does not mean every outcome is equally likely. A body released from a low-orbit station is far more likely to re-enter than to escape the solar system. One lost during an interplanetary departure is more likely to remain in solar orbit. One released from a probe already traveling faster than solar escape speed can continue outward. The vehicle's mission writes most of the first draft. Wherever the route leads, it decides which clock dominates. Atmospheric re-entry can destroy the remains in minutes. A sun-grazing orbit can erase organic material through heat. A stable, distant orbit may preserve a recognizable form, while radiation and impacts work slowly. An interstellar path can extend the story beyond the lifetime of nations, languages, and perhaps the species itself. That last possibility changes the emotional scale of the question. A human body might continue moving after every person who knew it is gone, after the spacecraft's mission is forgotten, and after the civilization that launched it has changed beyond recognition. Yet motion alone does not guarantee preservation. Time provides more opportunities for every slow form of damage already encountered. The destination and the condition cannot be separated. A body approaching a star does not remain the same object that entered darkness. One falling into an atmosphere trades vacuum for pressure and heat. One orbiting quietly still accumulates radiation and impact damage. The path continually chooses the environment, and the environment continually changes what follows the path. By tracing that motion, we finally see why there is no universal answer, measured only in years. The body's apparent survival depends on whether it is re-entered, burned, buried, shattered, or carried into a quiet region where change becomes almost immeasurably slow. Only after following that motion can we return to the final question. Not where the body goes, but how long anything arriving there would still be recognizably human. Recognition sounds simple until we ask what it requires. A distant observer might call the remains human because a helmet, 2 arms, and 2 legs still form a familiar silhouette. A forensic scientist might require identifiable bones, tissue, or DNA. Someone who knew the person would look for a face, a mark on the suit, or a feature that carried memory. Each standard can fail at a different time, which means there is no single moment when the body stops being human in every sense. The outer shape may be the last obvious answer. A pressure suit can hold the limbs in position even after the tissues within have dried and shrunk. Its rigid torso, helmet, gloves, and boots preserve the proportions of a person while hiding many of the changes beneath. Seen from far away, that figure could remain recognizable long after the body itself no longer resembles the moment of death. Closer inspection would tell a more complicated story. Skin may have tightened, cracked, or separated. Soft organs may have undergone early autolysis before cooling, and dehydration slowed them. Microbes may have altered protected regions while an intact suit held warmth and water. A shape that seems preserved can contain tissues that followed very different timelines, only centimeters apart. Anatomy may remain after appearance has changed. Bone, teeth, joints, and dried connective tissue can preserve the structure of a human body even when the face is no longer recognizable. The skeleton is a durable arrangement, but it is not permanent. Collagen weakens, minerals accumulate radiation damage, and impacts create fractures. The body can remain anatomically identifiable while becoming increasingly fragile. Identity may disappear earlier. DNA is sheltered within cells and can survive in protected tissues after death, but it is slowly fragmented by water, chemistry, radiation, and time. Cold and dryness can slow several of those processes, and bone or teeth may protect small samples. Nothing in open space guarantees a complete genetic record. A future probe might identify the material as human without recovering enough intact information to identify the individual. Even that distinction depends on the tools available. Modern laboratories can work with fragments that would have revealed little to earlier investigators. A far future civilization may detect molecular traces invisible to us, while a passing observer without specialized equipment sees only damaged fabric and bone. Recognizable always describes a relationship between what remains and the mind or instrument trying to understand it. The fastest endings provide the clearest limits. A body in low Earth orbit may re-enter within years or much sooner, depending on altitude and atmospheric drag. Heat and aerodynamic forces can destroy the recognizable form in minutes once re-entry begins. A collision with a large object or a high-speed impact on an airless moon can do the same in a single event. In these paths, space does not preserve the body for an age. Motion brings it quickly to a more destructive environment. A close approach to the sun offers another short answer. Increasing radiation and heat drive away remaining water, break down organic material, and eventually overwhelm the suit. Farther out, a planet's atmosphere may burn and scatter the remains, while a gas giant can carry them downward into pressure, heat, and chemistry from which no recognizable form emerges. The route can end the question before slow preservation has much time to matter. The longest answer belongs to a cold, quiet path, far from dense atmospheres, bright stars, and crowded debris. There, rapid decomposition may stop after the body loses water. The suit can continue holding a human outline, while dried tissue and bone change only gradually. Under favorable conditions, the form could persist for spans vastly longer than a burial on Earth would allow. But no scientifically honest clock can tell us exactly how many years. No human body has been placed on such a path, recovered after centuries, and examined. Vacuum experiments, microbial studies, exposed spacecraft materials, organic chemistry, and forensic research each provide part of the picture. Combining them shows which processes matter, but it cannot produce a precise expiration date for recognizable humanity. The uncertainty grows because the body does not remain in one laboratory condition. It rotates, crosses light and shadow, loses fragments, and moves through changing radiation and dust. A suit can leak at an unknown rate. An orbit can shift after a distant encounter. A single impact can expose material that had been sheltered for ages. Time is not the only variable. It continually creates new variables. This makes millions of years possible, in one limited sense, but misleading as a promise. A silhouette or arrangement of bones might survive for an immense period in a rare, quiet environment. The same remains could be destroyed tomorrow by a collision. Even without that collision, molecular damage continues. The longer the form survives, the less likely it is to preserve every deeper level of identity. The body therefore becomes less human by layers rather than by one clean transformation. Consciousness is lost within seconds. Coordinated life ends soon afterward. Familiar Earth-like decay may begin and then stall. Water leaves, soft tissue shrinks, DNA fragments, the suit weakens, and dust removes pieces. None of these moments alone provides the final boundary. Yet together, they move the remains away from a person and toward an object with a human history. That history can still be read for a long time. A suit design can reveal the era that launched it. Damage can show which side faced a star, where a particle entered, and how pressure escaped. Isotopes and materials can point back to Earth. Even when the face and genetic identity are gone, the remains may continue carrying evidence that they came from a technological species on a planet rich in water. If discovered by another civilization, the suit might speak before the body did. Fasteners, layers, manufactured alloys, and deliberate symbols cannot be explained by geology alone. Inside, a human skeleton would connect that technology to its maker. The finder might never know the name, voice, or story of the individual, yet could understand that the object had once been built around a living body. If found by future humans, the encounter would be more personal. They might recognize the engineering, reconstruct the trajectory, and trace it to a lost mission. They could discover that the body outlasted its radio signals, its records, and perhaps every person who remembered the launch. Preservation would then be measured not only in material survival, but in the distance between memory and rediscovery. There is no guarantee of discovery. A body is small against interplanetary space, and almost nothing against the galaxy. It emits no beacon once the equipment fails. Even if its path passes near another star, the chance that a telescope notices a dark human-sized object is vanishingly small. The remains can stay recognizable without ever being recognized. That difference changes the meaning of endurance. From the body's point of view, there is no waiting and no awareness of time. Years, millennia, and galactic orbits are only changes in the surrounding universe. Recognition matters to the living observer, not to the object. The body does not preserve itself for a future audience. It simply responds to physics for as long as its structure permits. Eventually, a sufficiently long future defeats every ordinary form. Radiation continues breaking molecular bonds. Dust continues making craters. Thermal cycles continue opening weaknesses where materials meet. A larger collision may arrive, or the orbit may lead into a star, planet, or atmosphere. The body is not exempt from change simply because the changes are too slow for a human lifetime to watch. As fragments separate, the definition becomes still harder. A glove containing dried tissue is recognizably connected to a person. A tooth moving alone through space may be identifiable as human under examination. A microscopic piece of collagen or mineral may carry biological information without carrying any visible form. Eventually, the pieces become too altered and dispersed for the word body to describe them honestly. The atoms remain. Carbon, oxygen, calcium, iron, and hydrogen do not lose their origin in a dramatic instant. They simply enter other arrangements. Some drift as molecules, some stay inside dust, and some may one day strike another world. They no longer belong to a coordinated human form, but neither have they vanished. Space destroys patterns far more readily than it destroys matter. This is the deepest answer to the question. A human body left in deep space does not explode, freeze forever in a perfect pose, or disappear according to one universal countdown. It passes through a sequence determined by pressure, oxygen, water, temperature, radiation, impacts, and motion. Some changes arrive in seconds, others in hours, and others may continue for ages. Under the right conditions, the body can remain visibly human for an extraordinary time. Under a different trajectory, that appearance can be erased almost immediately. The most important factor is not simply that the body is in space, but which part of space, inside what protection, moving along what path, and exposed to which events. Deep space is not one environment, so it cannot produce one fate. The quietest outcome is also the most unsettling. Far between worlds, the remains may become cold, dry, and almost unchanged to the eye, while their molecules continue aging. They can outlast the mission, the spacecraft that released them, and perhaps the civilization that remembers them. Yet that endurance is not immortality. It is change stretched across a scale so large that stillness becomes an illusion. At the beginning of this journey, the body seemed fragile because vacuum could take consciousness within seconds. At the end, it seems strangely durable because form can survive long after life, identity, and memory have gone. Both impressions are true. The human organism is exquisitely dependent on a narrow environment, while the material left behind can persist under conditions no living person could endure. So how long would it remain human? As a living being, only moments. As a recognizable body, perhaps an immense span under favorable conditions, though no exact number can be defended. As a genetic identity, likely less time than the outer shape suggests. As matter that once belonged to a person, it can continue for as long as those atoms remain in the universe. The answer depends on where we choose to draw the boundary. If humanity means awareness, it ends before the drift has truly begun. If it means anatomy, the boundary may survive across ages. If it means memory, the final human connection may disappear on Earth, while the body still turns silently beneath distant stars. Space does not decide which definition matters most. It only preserves and erases different parts at different speeds. What remains is neither a perfect monument nor an object instantly stripped of meaning. It is a changing record, held together for a time by tissue, bone, fabric, and motion. The universe may eventually scatter every part of it, but until that happens, the form carries one quiet fact through the darkness. A living world once made this body, and for a brief time, someone looked out from inside it. Thank you for watching this calm journey into what happens to a human body left in deep space. If you enjoyed this documentary, subscribe for more quiet space stories like this. Leave a like if you want more deep journeys into the mysteries of the universe. And tell me, which fate feels stranger, disappearing quickly near a world, or remaining recognizable long after humanity is gone? I will pin the most thoughtful answer. Tonight, you were watching the Just About Space channel, talking about what really happens to a human body left in deep space. Sleep well, and keep looking up. Good night.